Assalamu alaikum to you all. This is about Lab 11. Lab 11, as we explained before, is a continuation of Lab 10. So before you proceed with this explanation or listening to this explanation, I will suggest that you first read or you first watch the video recordings for the completion of the graphs lecture. These are already posted on the course page and also on YouTube. Basically, in the remaining part, we discuss about the remaining algorithms that that are taught in the course, mainly the topological sort and connectivity. Connectivity is actually the one that is really important as far as the practical aspect of this Lab 11 is concerned. You must understand the detail of the connectivity that we already discussed, and we also explain about spanning tree algorithms, two spanning tree algorithms, namely prims and Kruskal's. So I'm asking you here to do some practice based on those explanations already in the lectures. So please watch the lectures on graph 2, the concluding part of the lecture on graphs, before you continue with this lab. Now, if you recall from last week, we already explained everything about the implementation of graph, and you are asked to do the first two tasks as part of lab 10. And I said the remaining two tasks you will do in lab 11. Okay. The first one was a manual task, just a practice about breadth first traversal and depth first traversal. And the second part, which is the real practical one, is about connectivity, but this is for simple graphs or undirected graphs. Okay. So now I would like to explain about task number 3. Okay. So task number 3 says, add the following methods to the graph as list class. 1 is strongly connected. If you recall last time we did is connected. So it's connected is meant to be for undirected graph. And once you can reach all the vertices, if you start from a particular vertex, then the graph is connected, and all you did was to modify the breadth first traversal and count the number of vertices visited by your traversal. So now we are asked to implement another method called a strongly connected. Now, here I would like to remind you, as I already explained in the lecture, what is meant by strongly connected. For a strongly connected, it's not enough to start the traversal from only one vertex. Because if you remember, the definition says, for a graph to be strongly connected, there must be a directed path between every pair of vertices. Okay. So for example, here you see if you start from A, you can reach all the vertices. You can reach B, you can reach C through B, you can reach E, you can reach F, and you can even reach D, but you have to go the long way. You have to go B, E, F, D. So if you start from A, you can reach all the vertices. Is that enough to say this graph is strongly connected? Obviously not. Because, for example, as we explained, if you start from E, you cannot come back to B or C or A. And for us to conclude that the graph is strongly connected, you must reach each vertex starting from every other vertex. So what do you have to do, therefore, to implement that method? There are two things. First of all, A strong connected or a strongly connected is only applicable to directed graph. So the first thing I suggest you do in implementing this method is to call the isDirected method. If you recall in the graphers list, there is a method called isDirected that will tell you whether the graph is directed or not. Okay, this is for age. Actually, I'm looking for the one. No, it is the one I'm looking for. It is for the graph. Yeah, so you have to call this method and make sure it returns true. Okay, because we don't say undirected graph is strongly connected. No, that one is simply either connected or not. Okay, it is directed graph that has three states: strongly connected, weakly connected, and not connected. So the first thing you should do in your method is to call this method to make sure that the graph is directed. Good. So knowing that the graph is directed, what you have to do is you have to do a traversal starting from each vertex. For that, what I suggest you should do is you should have a method similar to what you did last time. If you recall, you did a method called isConnected. Yeah, here. Okay, now overload this method, but this time add a starting vertex as parameter so that we can call this vertex with vertex number 0, vertex number 1, vertex number 2, and so on. So you need a parameter here int start so that it will tell you whether the graph is connected if the traversal is started from a given vertex ID. Okay, now once you do that, in your strongly, you're going to call that so this method you are doing is just a helper method that can check whether the graph is connected if we start traversal from a certain vertex. Okay, so in your strongly connected, you are going to call that method in a loop. Okay, call it with starting vertex as 0, starting vertex as 1, and so on. If at any point that method returns false, then you can immediately stop and return false. Your graph is not strongly connected. However, if it continues to return true for all the starting vertices, meaning for all the vertices in your graph, from 0 to the number of vertices, then definitely your graph is strongly connected. So this is a hint about how to go about this. I repeat, first check that the graph is directed. If it is not, immediately return false. Second, you need to write that helper method, which if you give it a starting vertex, it will return true or false. Once you have that method, all you need here is a simple loop from 0 to the number of vertices. Repeatedly call that helper method and make sure you keep getting true. If you get false at any point, stop and return false immediately. But if after your loop you never get false, then you can conclude that your graph is strongly connected. This is basically how to do this method. Okay, the next method you are supposed to do is get undirected. Again, if you recall our definition of weakly connected, it says a graph is weakly connected if its underlying simple graph is connected. So this method that we're going to do actually is going to be helping us in doing this last one. Okay, so you can think of it as a helper method. Okay, the method is it returns an undirected version of the current graph. So it assumes that the current graph is directed, and it will return to you an undirected version of that graph. So basically what we want is, in this method you will create a new graph, okay, with the same number of vertices as the current graph. Okay, you know of course how to create a graph, just creating it from the constructor. I can show you quickly, for example, from the test class how we did it inside the init method. Okay, to create a graph, you just say new graph, and you give the size and a boolean value, either false or true. Since we are creating an undirected graph, of course the boolean value should be false. Okay, we are creating an undirected graph to represent the current graph. So new graph as list, the same size as the current graph, and false. Okay, so this is a new graph. It is empty, no vertices added, no edges added. So next is you have to add all the vertices of the current graph. Okay, so to add vertices, again, it's very easy. Just in a loop from 0 to the size of the current graph, call your graph.addVertex method. So this will add all the vertices of the current graph. Just call the addVertex method in a loop, the same number of time as the size of the current graph. Okay, so your graph will have had vertices now, but so far no edges. So the next thing to do is to add all the edges of the current graph along with all the opposite edges. Add the edges of the current graph along with their opposites. So if you look, for example, this is a directed graph. Suppose we want a undirected version of it. All you have to do is, for this edge AB, you will add it, but also you will add another edge BA. For edge CA, you will add it, but you will also add an edge AC. For edge BC, you will add it, but also add another edge CB, and so on and so forth. So for all the edges of the current graph, you have to add them, and you have to add their opposites. Now the good news is, from last week, you already did a method called getEdges. GetEdges. So you can call this getEdges to get the edges of the current graph as an array list. Then for each of them, you can use for each loop, because remember, you can use for each on an array list. So for each edge in your list of edges, you will add the edge as it is. Remember, an edge has method get v0 and get v1, so you can call those to get the v0 and v1 if you need to do that, because here you see, for example, to add an edge, you need to provide the v0 and the v1. What you have is an edge object, yani. So from that object, you can ask it to give it your v0. You can ask it to give it its v0 and its v1. Save them in variable because you're going to use them twice. You're going to add the edge v0 v1, but you're going to also add the edge v1 v0. Okay, so I repeat, get the list of edges in an array list, then use for each to get each edge. So for each edge in the array list, get the v0 and v1 of that edge. Save them in a variable. You can say int v0 equal to your edge dot get v0, and similarly for the v1. So once you have v0 and v1, to add an edge to your current graph, okay, the graph that you are trying to update, just call the add edge method twice, one with v0 v1 and the other one with v1 v0. So once you do this for all the edges in the current graph, then your new graph is complete. It's a complete undirected version of the current directed graph, and therefore you should just return it. Okay, you can see the return type of your method is graph as lists. Okay, so your method will return that graph. Okay, so in summary, to implement this method, you need to create a graph as list object, a new object. That object has no vertices, no edges. Okay, now add the vertices and then add the edges of the current graph along with their opposites, and then return the graph. Okay, this is basically what this method is supposed to do. We're going to need this method in doing the last task. Okay, the last task is weakly connected. We want to check if the current graph is weakly connected. So here is what you're going to do, or here are the conditions for the graph to be weakly connected. First of all, it has to be directed. So like we did in the strongly, you have to make sure that the graph is directed. So the graph is directed. This is condition number one. Condition number two, it is not strongly connected. Okay, so you can call this method and make sure you get false, because if it is already strongly connected, then it cannot be weakly connected. Okay, and finally, the undirected version of the graph, which you can get by calling this method, is connected. Okay, so just check that the undirected version is connected. You can use your is connected method of last week, because here we are dealing with an undirected graph. So an undirected graph, you don't have to start from all vertices, only from one vertex. Vertex 0 is enough. So you can call your method of last week to make sure the undirected version of the graph is connected. So in summary, this is actually just a combination of three Boolean values. One is directed, two is not strongly connected, and three, get undirected dot is connected. In other words, the undirected version of the current graph is connected. If you have these three conditions, then the graph is weakly connected. So just return true. So this is all you have to do to implement this method. Okay, check that the graph is directed, check that it is not strongly connected, and then three, get the undirected version of the graph and check that it is connected. So just say get undirected dot is connected. You can AND these three conditions. If all of them give you true, just return the result, otherwise return false. This is basically how to implement this tree method, and this is what you are expected to submit for lab 11. So you have to, of course, update your test graph to test your method. Okay, update the graph class to add an option to test and print the types of connectedness of the graph. For the undirected graph, the output should be either connected or not connected. So if you are testing your connectedness of last week, the output is simple. Either it is connected or not connected. But for directed graph, the output is one of three. Either you say is strongly connected, is weakly connected, and finally is not connected. If you look at the example graphs I gave you, definitely graph GD, the last one here, is strongly connected. If you start from any vertex, you can reach any other vertex. So you can use this to test for is strongly connected. However, graph GB is weakly connected. Because you see, for example, if you start the traversal from 5, you cannot go anywhere. 5 is an island. There is no vertex going from 5 to any other place. Okay, so if you want to test for is weakly connected, this is a good example. All right, now how do you test for not connected at all? This is easy. For example, you can take your GA, just change the size from 9 to 10 in the text file for the graph. Right now you see 9 is the number of vertices. Okay, if you open graph data A, you see that the size is 9. So if you want to check for undirected, just increase this to 10 and run the program. Because increasing it to 10 means there is a vertex number 9, but there is no edge to it, because these edges are all from 0, 1, 2, and so on until vertex 8. But there is no edge from 9 to any other vertex. Okay, remember, if you have 10, then the vertices will be from 0 to 9. If you have size 10, yani. If you have size 9, then the vertices would be numbered from 0 until 8. So by the time you make this to be 10, it means there are 10 vertices. The last one is number 9. Okay, obviously it is not shown in the graph here. And so there will be another vertex 9, but there is no edge connecting it from any of the vertices. So if you run the code, obviously it should say not connected. Okay, this you can do even from your work of last week. Now you can do the same thing for directed graph as well. Here, GD or GC, just increase the size by 1. It means we're going to have another vertex that is completely isolated. So your program should say this graph is not connected at all. Okay, this is how to test for not connected. Just increase the size by 1. But for weakly connected, you can use GB. GB is definitely weakly connected. And for strongly connected, you can use GD. So those are the things you have to do as far as the practical is concerned. Now, but here in this lab, we are also giving you opportunity to practice the algorithms that I discussed in the second part of the graphs lecture. If you look at the document, task number 4 is asking you to practice Dirichlet's algorithm, Prim's algorithm, as well as Kruskal's algorithm. These are all explained using nice animations in the lecture. So if you haven't studied the lecture yet, please do that. So the task is saying, or rather the task, although it's not to be submitted, it's just an exercise. So for the graph GC above, manually trace the execution of each of the following algorithms using the table provided. I have provided for you tables inside a document here called Algorithm Tracing Worksheet. Okay, if you open that worksheet, you see that there are tables for this is for cluscals, this is for prims, and a similar one for Dirichlet's algorithm for shortest path. So it's asking you to try finding or tracing those algorithms using the tracing sheet provided. We will soon be giving you assignment to do which are based on this algorithm. So the earlier you know how to do them, the better. And of course, in an exam, you could be asked to trace these algorithms. All right. So basically, this is what this lab 11 is about. It's an extension of lab 10 because it will be too much to expect you to do all of this in one lab. This is why it is broken into 2 labs. And I think that is all I have to say. This is going to be the last lab. So once you submit this one, there is nothing more to submit. I will stop here. Thank you very much.